Okay, so power and resistance. So we already know two equations which has got power in it. So we've got power equals energy over time, and we've got power equals current times by voltage. Okay, so now we're going to get some more equations with power in them, just to keep things complicated. So power and resistance. When a current flows through a resistor, electrical energy is converted into heat energy. The rate at which energy is transformed, measured in joules per second or watts, is the power of the resistor. So power of the resistor is current through the resistor times potential difference across the resistor. P equals IV. And that's the one that we just did the equation, the homework based on. We also know from Ohm's law, V equals IR. So voltage or potential difference is current times by the resistance. So what we can do is we can substitute in the V. So this V, IR, we can put in instead of this V here. So we end up with P equals IV, so P equals I times by IR. And if we wanted to make that a little bit neater, we've got P equals I times R, or P equals I squared R. And that is one of the equations that includes power in it. So alternatively, instead of V equals IR, you can rewrite that as I equals V over R. So instead of transplanting the V, we can transplant the I. So P equals IV. So we can get rid of that I and replace it with V over R. So P equals IV, so P equals V over R times by V. And again, not very neat. So it's P equals V times V over R, or V squared over R. And that is another equation which has got power in it. Lots and lots of equations that have power in it. But you'll be glad to see that over the page is a summary of the equations. So equation summary, P equals IV when the current and potential difference are known. P equals I squared R when the current and resistance are known. And P equals V squared over R when the potential difference and resistance are known. I'm just going to look at it right in just to make it complete. P equals E over T. Because that's another equation with power in it that you might come across in these kind of questions. And that's when energy and time are known. So the trick is with these, they're quite easy to use, but you just need to be able to identify which equation to use. So the best thing to do when we're doing power questions is write down everything that we know, everything that we've been told in the question. And then from that, work out which equations to use. So for example, a current of 280 milliamps flows in a lamp filament of resistance 16.5 ohms. Calculate the power of the lamp. Okay, so what are we given? Current is 280 milliamps. That should be alarm bells already. It's in milliamps. We need to change it into amps. Okay, so 280 times 10 to the minus 3, or 0.280 amps. So just be aware, if it's in milliamps, you will need to change it into amps. We've got a resistance. It's 16.5 ohms. And it's asking us to calculate the power. So power equals question mark. Okay, so then you look at those equations, right? Which one do I use? I've got an I, an R, and a P. Which one of those equations only has I, R, and P? This one, P, I, and R. So we'll use P equals I squared R. So we're finding P. I is 280 times 10 to the minus 3, and it's squared. Usually if anyone makes a mistake, they forget to square something, times by the resistance, which is 16.5. So you just put that into your calculator and you should end up with 1.29 watts. Okay. Have a go at questions 2 and 3. Just have a go at them and then we'll go through them as well in a second. So number 2, you've just been given P, I and R again. So you're going to use the same equation. So for number 2, P equals I squared R. So the power is 400. Current squared, well, you want to find current, so you just leave it as is, times by the resistance, which is 200 ohms. So current squared is 400 divided by 200, which is 2. So to find the final current, you need to square root 2, which is 1.41 amps. Everybody all right so far? Number 3, I can always put them back if you need me to. A 50 ohm resistor has a potential difference of 100 volts across it. What is the power of the resistor? So we're told the resistance equals 50 ohms. The voltage is 100 volts. And we want to know the power. So we don't want current in that equation now. So we look at that equation list. We find one with just R, V, and P in it. So P equals V squared over R. So V is 100, so 100 squared divided by 50, which comes to 200 watts. Number 4, just watch your units for number 4. An engineer is designing an electric heater element using a new type of wire. The power output of the heater should be 2.4 kilowatts. So that again should be alarm bells. You need to change it into watts. 2,400 watts. 2.4 times 10 to the 3 watts. The voltage is 230 volts. Just be careful as well with questions. Sometimes it might just say connected to the main supply and not actually give you a voltage. But by saying it's connected to the mains, you should then go, right, I know the mains is 230 volts. I know it was from electricity 1, which seemed like a long time ago. But you need to be able to be aware that mains is giving you a voltage, even though it doesn't actually say the voltage. And we want the resistance. So again, P, V, and R, P equals V squared over R. So 2,400 equals 230 squared divided by R. So R will be 230 squared divided by 2,400, which comes to 22.0 ohms. think I rounded it there. So number 5, a current of 4 amps flows along a flex of resistance 0.2 ohms to an electric heater, which has an element of resistance 60 ohms. Calculate the heat generated per each second in A, the flex, B, the element. So for this one, the heat generated is the energy. You know, heat is an energy. So you actually want to find eventually the energy produced in a second. But to do that, we need to know the power first of all. So for part A, the flex, we've got a current of 4 amps. The flex has a resistance of 0.2 ohms. And we want to know what the power is first of all. So we've got I, R, and P, so we're going to use the equation P equals I squared R. So 4 squared times by 0.2, which is 3.2 watts. But then to find the energy generated in a second, we need to use the equation power equals energy over time. So we worked out the power is 3.2. Energy is what we want to find, and it just says it in each second, which makes it nice and easy because time is 1 second. So the energy is just going to be 3.2 times 1, so 3.2 joules. Okay, so an extra step in that one. Do you want to have a go at B? It's just the same kind of thing again, but your resistance is different because it's the element rather than the flex. Current is the same. So it should be just telling you there as well that the power is the amount of energy transferred every second, or the amount of energy generated per second. So if it's asking you what's the energy generated per second, it is the same as the power. Okay, but if in doubt, just put it into the equation power equals energy over time, and that'll tell you the answer anyway. Right, are there any questions on these? Nope. Right, okay, so you can now do question booklet, pages 27 and 28. And also, I'm going to set you another Firefly homework based on all the power